Hello everyone. Till now we have solved the boundary layer equation using similarity method, where you convert the partial differential equation to ordinary differential equation and you can easily solve ordinary differential equations with given boundary conditions. Today we will learn one new method, which is an approximate method known as integral method. There are many situations where it is desirable to obtain the approximate analytical solutions. When can we have this approximate analytical solution? When exact solution is not available or cannot be easily obtained, and when solutions are too complex, implicit or require numerical integration. So, the advantage of these approximate solutions are the integral method is simple and it can deal with complicated factors. The integral method is used extensively in fluid flow, heat transfer and mass transfer. The mathematical simplifications are there in approximate solutions because number of independent variables are reduced. When you consider two dimensional situation, you can see that using integral method you can convert the partial differential equation to ordinary differential equation. So, you can see that there is a reduction in order of differential equation. So, in differential formulation we know that we consider one infinitesimal element of length dx and dy, and the conservation laws are applied to this infinitesimal element. So, the solutions are exact, whereas in integral formulation the element is infinitesimal in x but finite in y. In this particular case, when we consider boundary layer equations, you can see for a flow over flat plate, delta is the boundary layer thickness and your infinitesimal element is dx. So, the element is dx into delta. So, obviously we apply the conservation laws in an average sense, and hence solutions are approximate in integral formulation. Now, let us discuss what is the procedure we will follow when we use this approximate method or integral solution. First, we have this integral formulation of the basic laws. Okay. The first step is the integral formulation of the principles of conservation of mass, momentum and energy. So, first you see what are the governing equations for that fluid flow and heat transfer phenomena, then you write it in integral form. Next, you assume the velocity and temperature profiles. So, approximate velocity and temperature profiles are assumed which satisfy known boundary conditions. An assumed profile can be in the form of exponential. A polynomial is usually used in Cartesian coordinate. An assumed profile is expressed in terms of a single unknown parameter or variable which must be determined. So, in this boundary layer equation for flow over flat plate, we will see that this unknown variable is your boundary layer thickness delta, and finally you determine the unknown parameter or variable. So, conservation of momentum gives the unknown variable in the assumed profile, and conservation of energy gives the unknown variable in the assumed temperature. So, if you follow these three steps, then you can use this integral approach to solve the boundary layer equations, and we can find the velocity and temperature profile, as well as we can find the heat transfer coefficient and the Nusselt number. So, what is the accuracy of this integral approach? Since basic laws are satisfied in an average sense, integral solutions are inherently approximate. So, accuracy depends on assumed profile, which is not unique, because you can use third order polynomial or second order polynomial. So, accordingly you will get the velocity profile or the temperature profile. The accuracy is not very sensitive to the form of an assumed profile. So, you can see there will be little variation when you use different degree of polynomial in the final solution of temperature profile or velocity profile or the boundary layer thickness. There is no procedure available for identifying adjoint profiles that will result in the most accurate solutions. We do not know the optimum temperature or velocity profile for which you will get the results which is closer to the exact solutions. Today we will consider only fluid flow, because you know that in convective heat transfer we need to solve the fluid flow equation as well as the energy equation. In today's class we will solve the fluid flow equation using the integral method, and we will find what is the boundary layer thickness, then we will find what is the shear stress acting on the flat plate, and then we will find the coefficient of friction. So, now let us consider flow over a heated flat plate. First we will solve the fluid flow equation, then we will solve the energy equation for two different boundary conditions with constant wall temperature and with constant heat flux. So, you can see this is your heated flat plate, this is the x direction, perpendicular to the plate is y direction, you have free stream velocity u infinity and free stream temperature T infinity, and this is your edge of the boundary layer and this is the boundary layer thickness delta, obviously it is hydrodynamic boundary layer thickness, and the velocity profile will vary like this, where u is function of x and y, and here u infinity is the free stream velocity. So, let us write the governing equations. First is continuity equation, that is your del u by del x plus del b by del y is equal to 0. So, obviously we are considering a two dimensional case. Then you have boundary layer equation for flat plate, you know u del u by del x plus v del u by del y is equal to, there will be no pressure gradient because it is a flat plate, and you have nu del to u by del y square, and obviously energy equation you can write as u del t by del x plus v del t by del y is equal to alpha into del to t by del y square. So, obviously you can see nu is your kinematic viscosity and alpha is your thermal diffusivity. So, now you can see once to solve the energy equation we need to know the velocity profile, because in the energy equation you have the velocities. So, first let us solve this equation for the case flow over flat plate using this integral approach. So, already we discussed the first approach is that you have to integrate the governing equation. So, first we are considering the momentum equation, which is your u del u by del x plus v del u by del y is equal to nu del to u by del y square, right. So, now let us integrate this equation in the boundary layer, because 0 to delta. Okay. So, as we are using integral approach, obviously in y direction we are using delta and in x direction it is infinitesimal distance dx. So, if you integrate it, integrating the above equation between 0 and delta, where delta is your hydrodynamic boundary layer thickness. So, you can see you can write 0 to delta u del u by del x dy plus 0 to delta v del u by del y into dy is equal to 0 to delta nu del to u by del y square into dy. Now, we will consider this each term separately and we will integrate step by step. So, first let us give the term as 1 This is the first term, the second term is this one in the left hand side, and in the right hand side let us name as term 3. So, term 1 let us write as 0 to delta u del u by del x dy. Okay. We will take this u inside this derivative. So, if you put it inside the derivative, then you can write 0 to delta half del u square by del x into dy. Okay. So, you can see. So, if you take the derivative, obviously you will get 2 u and you will get back this term. Now, term 2. Okay. So, this is the term 2. So, this is your 0 to delta v del u by del y dy. So, now we will use integration by parts, okay, and you, because there are two variables v and del u by del y. So, use integration by parts. So, if you write it, so integrating by parts, what you will get? So, v into u, okay. So, del integration of del u by del y dy. So, it will get u only 0 to delta, okay, minus 0 to delta. So, now this is the first term. So, it will become del v by del y and this will get u into dy. Okay. So, now let us see the continuity equation. Okay. So, what is your continuity equation? Continuity equation is del u by del x plus del b by del y is equal to 0. So, this del b by del y term you can write as del b by del y minus del u by del x. So, you see this if you put the limit. So, if you put y is equal to delta. So, at y is equal to delta, what is the velocity? U will be u infinity, because that is the edge of the boundary. So, you will have u infinity. So, you can write u infinity v at delta, okay, this is unknown, and if you put the lower limit, so velocity at 0, so it will be 0 only. Okay. So, if you put del v by del y is equal to minus del u by del x, and if you multiply with u, and this u if you take inside this derivative, then you can write half del u square by del x into dy. So, the left hand side let us write all the terms. So, in the left hand side we have all the terms as 0 to delta half del u square by del x dy plus v u infinity v delta plus 0 to delta half del u square by del x into dy. Now, in this equation you can see v delta is unknown, right. So, what we will do now, we will again use the continuity equation and we will integrate between 0 and delta. So, these two terms if you put together, it is half and half. So, it will be 1. So, it will be just 0 to delta del u square by del x into dy, okay, and this we need to determine v delta. So, let us consider the continuity equation. So, continuity equation is del u by del x plus del b by del y is equal to 0, okay, and integrating between 0 and delta, okay, within the boundary layer thickness. So, you can see it will be 0 to delta del u by del x into dy plus 0 to delta del b by del y dy is equal to 0. Okay. So, now you can see this term will remain as it is 0 to delta del u by del x into dy, and this term. So, it will be integral 0 to delta dB. So, it will be just V 0 to delta is equal to 0. So, you can see, you can write as 0 to delta del u by del x into dy plus, so V delta at y is equal to delta, and at y is equal to 0 V is 0. So, minus 0 is equal to 0. So, you can find the V delta as minus 0 to delta del u by del x into dy. Okay. So, this V delta now you put here. So, now left hand side you can see, you can write as 0 to delta del u square by del x dy. So, V delta let us put there. So, it will be minus u infinity 0 to delta del u by del x into dy. Okay. So, you can see in the first term. So, in the first term you have del of del x u square dy, right. So, this now we will use the Leibniz theorem, okay, so that we can integrate this term which is having derivative, and we can take this derivative outside the integral. Okay. So, you can see the Leibniz integral rule gives a formula for differentiation of a definite integral whose limits are functions of the differential variable. So, if you have d of dx integral a to b, where a is function of x f x by dy. So, you can write integral a to b del f by del x dy plus f at y is equal to b db by dx minus f at y is equal to a dA by dx. Okay. So, a and b are the limits and function of x. So, now you see in our left hand side the first term. So, u square you can take as f, right. So, you can see that this f, okay, x y. So, this you can take as u, and this limits obviously you can see a x. So, this is your lower limit. So, it is 0, and the upper limit in our case it is delta, and which is function of x, okay, and obviously u is function of x and y. So, now you can see that in the left hand side we have this term. Okay. So, this we want to write this derivative with respect to x, we can take outside the integral using this Leibniz theorem. Okay. So, you can see now, so you can see we have this term as well as this term, okay, del u by del x. So, f will be one time u and another time will be u square, and we will take the derivative outside the integral, and another time f x y we will take u square. Okay. So, now you can see if you put this f x y as u, then you can write d of dx 0 to delta u dy is equal to 0 to delta del u by del x dy. Now, f at x equal to b. So, now u at x equal to at y is equal to delta. Okay. So, you have to see that f at y is equal to b. So, in this case u at y is equal to delta. So, what is that? That is your free stream velocity u. So, you can write plus u infinity, and what is b? B is your delta. So, d delta by dx, okay, and minus. So, this is your at y is equal to 0. So, that is your 0, right. So, a is also 0. So, this term will become 0. Okay. So, you can see, you can write 0 to delta del u by del x dy is equal to d of dx 0 to delta u dy minus u infinity d delta by dx. Okay. And if you use f x y as u square, then what you can write, d of dx 0 to delta u square dy is equal to 0 to delta del u square by del x into dy, okay, plus this function at y is equal to delta. So, that is your u infinity. So, it will be u infinity square d delta by dx, and at y is equal to 0, obviously it is velocity is 0. So, it will be 0. Okay. So, you can see, you can write 0 to delta del u square by del x dy as d of dx 0 to delta u square dy minus u infinity square d delta by dx. Okay. So, you notice these two equations. So, now inside the integral we had partial derivative, but using this Leibniz integral rule, you can see you have used ordinary derivative d of dx and d delta by dx, similarly for these equations. Now, you put this expression in the left hand side terms. So, we can write finally. So, left hand side we had 0 to delta del u square by del x into dy minus u infinity 0 to delta del u by del x into dy, right. So, now this using Leibniz rule, whatever you have got, so that you just write it. So, this we have written d of dx 0 to delta, okay. So, you can see this is u square dy. So, it is your u square dy minus u infinity square d delta by dx, right. And now integral 0 to delta del u by del x dy. So, that we will put the value. So, it will be minus u infinity d of dx 0 to delta u dy minus u infinity d delta by dx. Okay. So, from Leibniz integral rule, whatever we got the partial differentiation inside the integral, that we have written in terms of the ordinary derivative outside the integral. Okay. So, that we have just put the terms in this expression. So, now if you rearrange, you can see. So, it will be d of dx 0 to delta u square dy minus u infinity square d delta by dx. So, this you multiply with minus u infinity. So, you will get minus d of dx 0 to delta u into infinity into dy. I put inside this integral u infinity because u infinity is constant. So, you can take also inside the integral, and this minus and this minus will become plus. So, it will be u infinity square d delta by dx. Okay. So, you cancel these two terms, it will. So, you will get d of dx, okay, 0 to delta. So, it will be u square minus u into u infinity dy, okay. And you can write minus d of dx 0 to delta u into u infinity minus u dy. Okay. Now, let us consider the third term, which was in right hand side of the boundary layer equation. So, if you see the third term, Okay, so that is in the right hand side. So, you have 0 to delta nu del to u by del y square into dy. Okay. So, what you can write this 0 to delta nu, you can take it outside because this is your fluid property and constant. So, you can write del of del y del u by del y into dy. So, you can see, so these del y will get cancelled. So, you can write this as nu del u by del y, okay, 0 to delta. Now, you see that at y is equal to delta, which is your edge of the boundary layer. So, what is the velocity gradient del u by del y? Because at the edge of the boundary layer and outside the edge of the boundary layer, you have a free stream velocity u infinity. So, velocity gradient becomes 0. So, that means del u by del y will be 0 at y is equal to delta. So, you can see at y is equal to delta, it will be 0 and minus nu, and del u by del y at wall will have some value, right. So, that is y is equal to 0. Now, this term we can represent in terms of shear stress, wall shear stress, right, in terms of wall shear stress tau w. So, you can write wall shear stress so tau w is your mu del u by del y at y is equal to 0, right. So, you can see, you can write del u by del y at y is equal to 0, you can write as tau w by mu. Okay. So, now you see the left hand side term is this one, which has one negative sign, and right hand side this is the term, and if you put the value of del u by del y at y is equal to 0, you will get as minus. So, nu is your, what is nu? So, nu is your mu by rho, right. So, you will get 1 by rho tau w, right. So, you can see you have minus. So, now if you write left hand side is equal to right hand side. So, what we are going to get? So, if you put left hand side is equal to right hand side. So, we will get minus d of dx 0 to delta u infinity minus u dy is equal to minus tau w by rho. Okay. So, you divide both side by u infinity square. Okay. So, divide both sides by u infinity square. So, and this minus and right hand side minus will cancel. So, you can write d of dx 0 to delta. So, this u infinity square we are dividing here. So, you can write as u by u infinity, one infinity we have divided with u, and inside you divide another u infinity. So, it will become 1 minus u by u infinity into dy is equal to tau w by rho u infinity square. Okay. So, this equation is known as momentum integral equation. Okay. So, we started with the momentum equation, we integrated between 0 and delta, and finally, we have arrived in this expression. So, you can see this is known as momentum integral equation, and you can see that this is your ordinary derivative d of dx. Now, we need to assume the velocity profile. Now, we need to go to the second step. So, we need to approximate the velocity profile. Now, let us assume the velocity profile. So, assume velocity profile. Okay, so we will use polynomial expression. So, u x y will take as summation of n is equal to 0 to capital N C n, which is the coefficient function of x and y to the power n. So, today we will consider third degree polynomial. Okay. So, if you consider third degree polynomial, then you can express this velocity profile as third degree polynomial. Okay. You will get u as C0 plus C1 y plus C2 y square plus C3 y cube. Okay. So, considering third degree polynomial, we got 4 coefficients. Okay. So, we need to determine C0, C1, C2 and C3. So, how many boundary condition do you require to find these 4 coefficients? Obviously, you need 4 boundary conditions. Okay. So, now you can see easily you can find 2 boundary conditions at y is equal to 0, no slip boundary condition. So, u is equal to 0 and y is equal to delta, you have u is equal to infinity. Another boundary condition at y is equal to delta, you can easily find that velocity gradient is 0. So, that means at y is equal to delta, del u by del y is equal to 0. So, these 3 boundary conditions you got easily. So, we need another boundary conditions. Now, the fourth boundary condition will derive satisfying the Navier-Stokes equation or satisfying the boundary layer equation at the wall. Okay. So, at y is equal to 0, let us see whatever boundary layer equation you have, what expression you get, and from there we will get the boundary condition. That is why it is known as derived boundary condition. So, let us write the boundary conditions. Okay. So, at y is equal to 0, you have u is equal to 0, at y is equal to delta, you have u is equal to infinity, that is your free stream velocity. At y is equal to delta, your velocity gradient is 0. So, del u by del y is equal to 0, and at y is equal to 0, now we will see the boundary equation is u del u by del x plus v del u by del y is equal to nu del 2 u by del y square, right. So, this is your boundary layer equation. Now, you put at y is equal to 0, what happens? Okay. So, we will derive this boundary condition. So, at y is equal to 0, u is 0, at y is equal to 0, v is 0. Okay. So, you can see left hand side 2 terms are 0. So, you will get del 2 u by del y square is equal to 0. Okay. So, this is your derived boundary condition. So, del 2 u by del y square is equal to 0. Okay. So, now you have 4 boundary conditions. So, find these 4 coefficients. So, we have u as C0 plus C1 y plus C2 y square plus C3 y cube, right. So, del u by del y, if you take the derivative with respect to y, so you find the del u by del y as C1 plus twice C2 y plus 3 C3 y square, and del 2 u by del y square you will get twice C2 plus 6 C3 y. Now, apply those boundary conditions. So, at y is equal to 0, you have u is equal to 0. Okay. So, if you see this equation at y is equal to 0. So, these last 3 terms will become 0, okay, and left hand side u is equal to 0. So, that will give C 0 is 0. Then at y is equal to 0 you have del 2 u by del y square is 0. Okay. So, if you put it here y is equal to 0, left hand side this is 0. So, it will give C 2 is equal to 0, and now at y is equal to delta you have u is equal to u infinity, right. So, if you put it in this expression, so you will get u infinity, C 0 is 0, C 1 delta plus C 2 is 0. So, C 3 delta cube, okay. And at y is equal to delta you have del u by del y is equal to 0. So, if you put here, so left hand side is 0 is equal to C 1, C 2 is 0. So, you will get plus 3 C 3 delta square, okay. So, you can see you can find C 1 is equal to minus 3 C 3 delta square, right, and if you put it here, so you will get u infinity is equal to minus 3 C 3 delta cube plus C 3 delta cube. So, what you will get? So, you will get, you see here minus 2 C 3 delta cube. So, C 3 will be minus 1 by 2 u infinity by delta cube, okay. So, C 3 is equal to minus half into u infinity by delta cube, and now C 1 you can write minus 3 minus half u infinity by delta cube into delta square. So, what you will get? So, it will get plus, so it will be 3 by 2 u infinity by delta, okay. So, now you can write the velocity profile as u is equal to C 0 is 0, C 1 is 3 by 2 u infinity by delta and into y, then C 2 is 0, and then you have C 3, C 3 is minus half u infinity by delta cube into y cube. So, you can see your velocity profile, you can write u by u infinity is equal to 3 by 2 y by delta minus half y by delta cube. So, you can see that assumed velocity is in terms of a single unknown variables delta, and delta is function of x, okay. So, now we will go to the next step, okay. So, what is that step? Determination of this unknown variable. So, we have expressed the velocity profile in terms of hydrodynamic boundary layer thickness delta, which is function of x. So, now this unknown variable delta we need to find, okay. So, that will determine. So, for this we will use this momentum integral equation, okay. So, we have momentum integral equation which we have already derived, okay. This is your d of dx 0 to delta u by u infinity 1 minus u by u infinity into dy is equal to tau w by rho u infinity square, and we have velocity profile u by u infinity is equal to 3 by 2 y by delta minus half y by delta cube. So, now let us put this velocity profile in this momentum integral equation and find the unknown variable delta, okay. So, we will just use eta as the ratio of y and delta. So, eta will just take as y by delta. So, you can see at y is equal to 0, eta is equal to 0, and at y is equal to delta you will have eta is equal to 1. So, this limit if you put it here, so all this expression you put, so put u by u infinity as 3 by 2 eta minus half eta cube in momentum integral equation. So, what you will get? So, you will get d of dx, okay, 0 to 1, because we are writing in terms of eta, and also you can see we have y is equal to eta into delta. So, dy we can write delta into d eta, okay, because delta is function of x only. So, dy you can write delta into d eta. So, u by u infinity, so it will be just 3 by 2 eta minus half eta cube, then you have 1 minus u by u infinity. So, 3 by 2 eta plus half eta cube, okay. dy is delta into d eta and is equal to tau w by rho u infinity square. So, you can see here your delta is function of x only, right. So, this delta you can take it outside this integral, okay, because this you are integrating with respect to eta, which is your y. So, obviously you can take it outside the integral. So, you can write d of dx, okay. So, you can write delta, then 0 to 1. Now, you just multiply this. So, what you will get? So, you will get 3 by 2 eta minus half eta cube, then minus 9 by 4 eta square plus 3 by 4 eta to the power 4, then you will get 3 by 4 eta to the power 4 minus 1 by 4 eta to the power 6, okay, into d eta is equal to tau w by rho u infinity square. So, if you rearrange it, what you will get? D of dx delta, okay, 0 to 1. So, you can write as 3 by 2 eta, and this is your eta square. So, it will be minus 9 by 4 eta square, then you have minus half eta cube, okay. These two terms eta to the power 4 you can write as 3 by 2 into eta to the power 4 and minus 1 by 4 eta to the power 6 d eta is equal to tau w by rho infinity square. So, if you integrate now, so you will get 3 by 2 eta square by 2, right, minus 9 by 4 eta cube by 3 minus half eta to the power 4 by 4 plus 3 by 2 eta to the power 5 by 5. Then you will get minus 1 by 4 eta to the power 7 by 7, okay, and limits are 0 to 1 is equal to tau w by rho infinity square. So, now at eta is equal to 0, anyway all these terms will become 0. At eta is equal to 1, you just put the value, then what you will get? D of dx delta. So, you will get 3 by 4 minus 3 by 4, okay, minus 1 by 8 plus 3 by 10 and minus 1 by 28. okay, is equal to tau w by rho u infinity square. So, these 3 by 4 you can cancel. So, you can get. So, now if you rearrange this and you can get finally in the left hand side as d delta by dx, okay, you will get finally in the left hand side 39 by 280, okay, and in the right hand side it is tau w by rho u infinity square. Okay. So, now let us find what is the wall shear stress, because wall shear stress you can express in terms of the velocity gradient at y is equal to 0 and velocity profile already you have derived. So, you will be able to find what is the shear stress. So, you can write tau w is equal to mu del u by del y at y is equal to 0, and you can see you can have velocity profile u by u infinity as 3 by 2 eta minus half eta cube, and also we have dy is equal to delta into d eta, right, because eta is equal to y by delta. So, you can write mu del u by delta d eta at eta is equal to 0, okay. Then you can write mu by delta and you can see. So, del u by del eta, okay, what we will get u infinity into 3 by 2 minus 3 by 2 eta square, okay. So, you can see del u by del eta at eta is equal to 0. So, you will get 3 by 2 into u infinity. So, finally, tau w you can write as 3 by 2 mu u infinity by delta. So, now if you put tau w here, so you will get, so you can write d delta by dx 39 by 280 is equal to, now tau w you are putting, so 1 by rho u infinity square and tau w is 3 by 2 mu u infinity by delta, okay. So, you can see you can write delta d delta by dx is equal to nu by u infinity, because you have infinity square here 1 u infinity. So, you can nu by u infinity and 280 by 39 into 3 by 2. So, this will be 13, this will be 140. So, you can write delta d delta is equal to 140 by 13 nu infinity dx. Okay. So, if you integrate this equation, so you will be able to find the unknown variable delta, okay. And you know that x equal to 0, you have the hydrodynamic boundary layer thickness as 0. So, that means delta is 0. So, if you integrate it, so you will get delta square by 2 is equal to 140 by 13 nu by u infinity x plus some constant, okay, c. So, now you put at x is equal to 0, delta is 0, right. So, that means it will give c is equal to 0, okay. So, if you c is 0, so you can write delta as, so you can write delta square by 2 is equal to 140 by 13 nu by u infinity into x. So, if you rearrange, you will get delta square is equal to 280 by 13 nu by u infinity into x, or you can write delta square by x square is equal to 280 by 13 nu by u infinity x. So, now you see in the last term you have nu by u infinity x. So, that you can express in terms of Reynolds number, okay. So, if you define the Reynolds number Re as u infinity x by nu, which is x is your axial direction. So, at x equal to L for the plate length L, you can write REL as u infinity L by nu. So, if you put it here, so you can see you can write delta by x as root 280 by 13 1 by root RE x, or you can write delta by x is equal to 4.64 by root RE x. So, now we have found the unknown variable, the hydrodynamic boundary layer thickness delta. Okay. So, now once delta is known, now you will be able to calculate the velocity profile, okay, because velocity profile we have expressed in terms of delta. So, now delta you have found, so you will be able to find what is the velocity profile using the integral method. Now, let us find the coefficient of friction. Okay. So, we have found the shear stress tau w as 3 by 2 mu u infinity by delta, right. So, now you can put the value of delta here. Okay. So, what you will get 3 by 2 mu u infinity, okay, and delta value you can see here. So, delta you can write as 4.64 x by root RE x. Okay. So, if you put this, so you can see you can write as, so now you can write tau w by half rho infinity square, which is your friction coefficient Cf, you can write as, so tau w is 3 by 2 mu by u infinity divided by half into rho infinity square. So, you will get root RE x divided by 4.64 into x. Okay. So, you can see here these 2 you can cancel. Now, you will get 3 by 4.64, okay, and here you see it is, so it will be just u infinity x and mu by rho is nu. So, this is your nu and 1 root RE x. So, you can see this is your 3 by 4.64, this is your 1 by RE x and this is your root RE x. Okay. So, the friction coefficient you will get as Cf, if you rearrange it you will get 0.646 by root RE x. So, today we considered the flow over flat plate and used approximate solution method to find the boundary layer thickness as well as the friction factor using assumed velocity profile. So, in integral approach there are 3 steps. First step is that you have to integrate the governing equation, then you assume the velocity profile and next you find the unknown variable. So, using the integral approach we have found delta by x as well as the friction coefficient Cf in terms of the Reynolds number, and finally you can see that if you compare the results you got from the integral method with the exact solution. So, there is, if you see this is your almost 10.8% error, and if you compare the Cf it is 2.7% error. Okay. So, you can see finally we have derived the hydrodynamic boundary layer thickness using integral solution delta by x is equal to 4.64 divided by root RE x. Similarly, coefficient of friction we have derived Cf as 0.646 root RE x. So, you can see these are approximate solution because we have used some approximate velocity profile, whereas you have the exact solution from Blasius solution you can see delta by x is equal to 5.2 divided by root REX and CF is equal to 0.664 divided by root REX. So, you can see both solutions have same form. If you compare delta by x with this integral solution and Blasius solution, you will get error in delta as 10.8% and error in CF is 2.7%. Obviously, error in CF is less than the error in delta, and accuracy of CF is more important than delta in design point of view. Thank you.